Ciao, Amir. I'm
Hello.
sorry that you cannot see all the room because it's full. There is a way to show the room. Giuseppino, ci sta un modo di fargli vedere la stanza? Ma neanche se giro il computer? Aiutami, dai. I want to show you the room because it's full of people. Wait,
Yeah.
just a second. Do you see something?
Wow, yes. Hello, everybody. Hello.
You're so nice. I
Nice.
love you.
Wow.
Thank you. Do again. Ciao. You see?
Yes, it's
Okay.
wonderful that
You
everything is
could
there.
come, Amir. There are people coming from Australia. Can you imagine? From Canada,
Wow.
USA, India, China, and from everywhere. Where are you
If
right now? In which
if I
country?
know, I would have come. I am from Israel, from Tel Aviv.
You are in Israel. It's there. I mean, it's in front of Italy. So you could
Yeah,
just
yeah.
jump here.
And I love Italy. I was in Italy like 10 times, so I wish I could come.
That's okay, but just to tell you that the room is full of students, of colleagues, of researchers from all over the world. And so I'm very happy that you can present your company. We just ended a session on quantum computing. Obviously, our topic is more related to quantum machine learning applied to Earth observation, as I explained you. But go ahead with the presentation of your company. You have a big audience, so share your thoughts and thank you. You are already online. If I close the microphone, everybody will listen to him, right? Okay.
So, hello everybody. It's really great that you are hosting me. It's a great privilege to speak with everyone. My name is Amir Naveh. I am one of the co-founders of a quantum computing company called Classic. And Classic is developing software for quantum computers, software and applications. We are now 70 people. Most of us are in Israel. Some of us are in the United States, in Europe, and in Japan. Maybe I have a kind of 3 presentations that I am considering on sharing. And what I would like to ask maybe is, what is the background in quantum computing for the audience? Do you know something? Do you know?
They know a lot because they listen to us for 2 hours. So you go ahead, don't worry,
Okay.
and share your screen and present whatever you want. You are talking with the smartest people in the world in this moment. So don't worry, in 2 hours, they learned everything about quantum. So don't worry, go ahead.
Perfect. So what I will do, I will share maybe something like 10 minutes about our company. After this, I will show you a live demonstration of how to create quantum algorithms, quantum software with our platform, which is open for academic usage. So as long as you are not doing commercial usage, you are able to access this for free and just explore and experiment in quantum software. And lastly, I will try to give some potential applications about remote sensing. In my past job, I was working in the Israeli Defense Ministry for Israel has quite a few satellites, and some of the satellites are synthetic aperture radar satellites. So I was one of the algorithm engineers in the past for kind of doing all kinds of smart analysis of the synthetic aperture radar images, doing a coherent change detection, if you heard about these polarimetric changes, etc. So I will try to kind of connect these 2 worlds of remote sensing and quantum computing. It's not the core of what the company does, but I think it would be an interesting closure.
Amir is perfect, so go ahead.
Let's begin. So first, let me present the company. Okay. So, just a minute. Okay. Good. So, so quantum computing in general is it's a whole new paradigm of how computers will work. Okay, so it will have impact, I believe, on almost every industry in the world that uses computational power, because it is just a fundamentally different logic that is believed to be, I believe to be much more powerful than what classical computers can do. Some of this is proven, some of this is maybe more of heuristics, but the underlying logic is completely different. So this could become a radically new technology here. And what is happening in the past, let me say, maybe 10 years more or less, is that we see more and more companies doing quantum hardware. Okay, so the companies are many large companies, Google, Microsoft, IBM, Intel, but also small startups, or even some that are not that small anymore, Pascal, QEra, Quantinuum. They are all developing quantum hardware in different modalities. Some are doing superconducting qubits, some are doing individual atoms, some are doing with photons. So a lot of different technologies. And this is from roadmaps of these companies. You can see that quite a few of them are expecting that we will reach some potential advantage or some really exciting applications in the next few years. So this is an exciting time to be developing quantum in general. And here is what our company does at a high level. So one thing is the quantum hardware, of course. You need to build the actual machines that work on these things called qubits, which I assume you've heard about a little bit. But once you have the hardware, it's not enough. You need some way in order to build software. Now, if you are an experienced quantum researcher in this field, you will be able to sometimes build small quantum circuits, so like examples, toy models. But if you are trying to solve anything that is of scale, you need abstractions that enable you to describe what is the program you are trying to achieve. So this is not really possible today with most technologies. And this is what Classic is doing. So I presented the company a little bit. We are a team of 65, almost 70 people, raised over $63 million. We have quite a lot of customers, both from enterprise and most of the universities in the world are using our platform to create quantum software. So this is a bit about us. And so the platform, I will share it in a minute. I will guide you on how to do things. But generally, what you do, you go to our platform. You can either work in Python or in a web application. It's the same. It has the same functionality. So in the web application, you just go to platform.classic.io and you press here sign up if it's your first time. And then I will show this to you live in a minute. But what happens is, okay, you're trying to describe some quantum program. So here is a very simple quantum program doing some, well, it's arithmetic. It looks familiar, right? We're multiplying x by 2, we're adding y, we're doing a maximum of some numbers. So this would be very easy for a simple like Python code or regular computer. But when you're doing it with a quantum computer, it's actually quite complex. So this is how the actual program would look. So it's each of these horizontal white lines, they are representing qubits or groups of qubits. And each of these yellow boxes are representing some function that happens to these qubits. It's kind of like playing the piano in some way where you have notes that are moving from left to right. So this is, we're playing, the notes are the functions, and we're kind of acting with the functions on the qubits. And you can see that within each of these individual layers is kind of subgates, and it's many different levels of hierarchy of how to actually create this program. And then you want to run it. So also in the web application and also in the Python, what you could do after you have this software is you press on this right-hand side, you press the yellow execute button, and then you get all of the different hardware providers that I just showed in the previous slide with all the different technologies. You can see how the program would run on them. So quantum computers today, they don't solve wide-scale problems. You cannot use them to actually optimize and you know, a new route for mail delivery, or for a new algorithm for image processing, etc., because they are not strong enough, the computers. But you can understand how much resources you would need on each of the computers, and for small-scale problems, you can actually run them. So on the previous problem where we only used a few qubits, you can actually run it on, for example, machines from IBM, and this is all quite simple, and you would get, okay, so this is how the algorithm maps onto the qubits in this actual hardware, and then you would see results. So this is, in this case, the state vector results for this specific arithmetic function. It has no meaning, it's just an example, but it's kind of showing you end-to-end how this works. So what the platform does in a nutshell is it enables you to build quantum algorithms, quantum software, from describing the algorithm, either in Python or in the web application, creating the actual program and running it on any hardware simulator, etc. And this is useful today because you can run it and experiment and actually run on small hardware devices and on simulators. But in the future, this would be how you actually access these quantum computers to solve real problems. Just a word about maybe what we are working with. Maybe I will talk mainly about academia here. It's more relevant. So Classic is working with hundreds of universities, many thousands of users, and what they are doing with the platform generally is well, research, right? So you have some new idea of an algorithm, or you're implementing some new application. You need in some sense to have the quantum program ready, and the Classic platform is probably the best solution for you to create the implementation, execute it if you need. Also some cool features like it exports automatically into a LaTeX. So if you want just the drawing of the circuit into your paper, you can do this really easily. It has some easy integrations with some other popular interfaces like IBM Qiskit or Microsoft Q#, so you can upload your circuits from these platforms as well, and kind of use only the execution or only the visualization parts. Let me see if there is something important here. Maybe one more slide that I wanted to show generally about quantum, not necessarily about Classic, and then I will jump to the demonstration. So let me share a different presentation with you. Okay. Just a minute. Okay. So this is an important slide. If we have time, there are quite a lot of interesting things to talk about, but I have one slide which I don't want to miss. Okay, this one. So this is, for me, an important slide in kind of understanding how I think the world works. So in 1945, we created a transistor. Okay, and this transistor initially in the ENIAC, well, it was after, actually a bit after the 40s, the transistor was a little bit after, but the first digital computer was ENIAC, built in 1945. And it was built to kind of compute the trajectories of artillery and the large guns, which they couldn't get accurately, and they needed large computational tables. That was what the first computer was built for. Fast forward 70 or 80 years later, and computers are powering the world. No large organization can survive even one day without computers. All of our society is based on computers. Everything we do is dependent on deep computational tasks that no one could even have imagined in the 1940s and 50s when this technology was first built. Sputnik was launched, if I'm not mistaken, in 1957. Correct me if I'm mistaken here in the years. And it just did a blip, blip, and it was kind of a technology demonstration that we can launch something into the atmosphere. Did a few circles around the Earth and deorbited, burned up in the atmosphere. Fast forward 60, 70 years later, we have a global positioning system based on satellites where you can pinpoint your location accurately in the resolution of meters. And then you have autonomous vehicles that are based on this location that can drive you anywhere without a driver, or it will come soon and you can share your location with your friend, like Harry Potter magic from these satellites. And of course, using the transistors from the earlier chapter. And my takeaway from this is that when you have fundamental technology leaps, don't really expect to understand from the get-go what you are going to achieve with them. Technology can do amazing things. Quantum computing is the sort of technology that does this binary leap for humanity. So when we implement this quantum hardware at scale, then some applications we already know. We know it's useful for optimization problems, for cryptography problems, for several other problems. But I think the vast area here is the applications that we don't yet know. And this is why it's an exciting field, because just like, you know, Shannon and Turing and von Neumann 8 years ago, which were real pioneers in classical computers, and everyone now knows their names as people that really drove an industry forward. Now in quantum, we have this opportunity. So someone that is now devoting their time and energy to building quantum algorithms and applications, this is kind of the things that will drive the world forward in the coming few decades, I believe. So it's an exciting opportunity. It's personally why I am excited about this field and this technology. So this was a slide important for me to share. Let me jump to the platform, unless if there are any questions, now is a good time actually.
Do you like if we ask for some questions?
Yeah, go ahead. I will share
I would like, you know, to involve the people here.
Yeah, if there are any questions, I'm happy.
Okay.
Very happy to answer.
So please, someone curious to ask something, please come. No, please come here. I want to introduce you first, and then we sit down so he can see you. I would like to know your name, and where are you coming from?
My name is Kawai. I'm born in Hong Kong, but I work in Australia. I think I'm one of the very few people not a PhD student or postgrad, not academic, but I'm working full-time in remote sensing industry in Australia, mainly focused on carbon market. Because it's a new market in Australia, government created the pool, and then there's not enough professional in this field. And all my colleagues, actually none of them are, maybe 2 of them are from remote sensing background, but most of them from geology, ecologists. Then yeah, we are lacking the skills to really scale up the research question we try to fund and then really bring the impact to the ground. Because we are working with the farmer in Australia to really try to make a difference to fight the climate change. But like, yeah, so I'm in a odd position. I'm not academic, but I'm not too commercial, but working in green industry. Yeah. So my question is like, in the previous slides, other presenters shared, say, quantum computer have a certain amount of error. How would your company handle this error is my first question. And my second question is, your platform is free for students, but from a commercial background, I think it's very important for us to know the cost, because for all my manager, they always ask the first question, how much? And then, can you test locally? And then if you click something wrong, how do you control the error cost? Thank you.
Okay. Thank you for asking, and it's great to meet you. About the first question, yes, this is true. The main problem today so there are already computers with 1,000 qubits, for example, but they don't work well because they have a lot of errors. So in our company, we deal with this in two ways. One way is to understand that at least in the coming few years, errors are going to be a part of quantum software, and this kind of limits the algorithms you can create. So you need to create algorithms that are very shallow in what we call depth, or number of gates. And part of what we do is optimize the size of the program so that you will get some signal even when the hardware is noisy. So this is relevant for the coming few years. Looking forward, what we expect is that when at some point you will be able to do what we call quantum error correction. This is theoretically possible, but it needs more advanced hardware. And with enough qubits, you can kind of correct the errors of the hardware and achieve something that is close to perfect. But to do this, the computational cost is very high. So part of what our software is doing is being able to do this error correction with fewer resources. So once you have a large hardware, then hopefully with our software you can run more advanced applications on it, or run some application faster on a hardware that is not strong enough yet, using this quantum error correction. So this is about the first question on errors. Regarding pricing, so I'm not the businessman of the company, so I'm not, I don't want to say a number, but quite a lot of companies are working with the platform. Also, when it's commercial usage, we have a large team that is working with customers to make sure that they are satisfied. So you can send an email to me, or just go to our website, classic.io, and there will be a button there, and you say contact us, and then I promise you someone from the business team will contact you, because they like money. So they will very fast, they will answer and tell you everything you want to know about costs.
Thank you, really. So you are coming, you are the closest one, right? You came from Australia. Australia is there. Thank you so much. Other questions? Please. I introduce first the person, Amir, just to explain to you. Okay?
Yeah,
and then she or he sit down, otherwise you don't see the person. Please tell your name. Tell your name and also where are you coming from, so everybody can, start knowing each other.
Hello, I'm Mobina. I'm Iranian. I study in Romania in a Marie Curie project with Professor Mihai Datcu. He is my supervisor. And hello, Amir. It was really interesting, the topic that you work. And but I found something interesting because I also work on SAR data and change detection. And I had a second one in Israel, but because of political things, I couldn't come there. And I want to know really how you integrate quantum computing like in your work, and what are the challenges or like the advantages, and which type of SAR data set for testing, and I appreciate if you please.
Perfect. Yeah, okay, good. So first maybe I will kind of, I just made a slide that is kind of relevant here. So let me just go to the top. It's not a very good slide, but I made it for now. So kind of there are, I think, quite a few applications for quantum computing in remote sensing applications, for image processing, for radar processing, which I know a little bit better, for optimization problems. So all of these may have applications. Just as a disclaimer, when I was working on SAR imagery and data, I didn't do it with quantum computers. This was like my previous job like 6 years ago. So, and as far as I know, well, I mean, it's almost by definition, quantum computers don't really help today because, again, they are not strong enough today. But let's look a little bit into the future, how this would work. So when you're doing, let's look at SAR reconstruction, for example. So you have several different methodologies of like doing matched filters or doing the slice projection theorem. But in the end, what you have is a whole lot of data. And sometimes it's quite noisy, and sometimes it's incomplete. And with all the different methodologies you do, it doesn't matter if you're working in the Fourier space or whatever, in the end you have some fitting problem here, where you have some large number of parameters, you have a model of the world which is not perfect, and you're trying from all of this to reconstruct a perfect image. And now imagine, I'm not saying this is the case, but imagine you had an all-powerful computer, something that you have unlimited computational resources, okay? It's not exactly the case with quantum. There are some things that you can do better than others, but imagine this like infinity supercomputer, okay? So everything from optimizing the parameters to being able to work with more parameters, to being able to make your model more elaborate, but still be able to train it in a normal amount of time, to just having every single iteration. So sometimes I remember back when I was working on this, that a single processing iteration could take sometimes hours when you really cared about the resolution. Imagine this goes down by orders of magnitude. Now, each of these problems needs to be well fitted into a quantum algorithm. It's not like plug and play. But the frame of mind I'm trying to emphasize is that as long as you have large computational problems that require intensive resources, sometimes in a proven way and sometimes in a heuristic way, this new logic could come to your aid. So this is kind of the high-level answer. Of course, I mean, we can go into sometime the equations of like how you would actually do the reconstruction, but I'm also a little bit rusty on the SAR reconstruction, so it would require some time for me. Maybe it's the last minute, so maybe just one final note from me, and I'm happy to take more questions if you have the time. But
Amir, I have more than a question, an observation to do together with you. Before you join our session, let's say, we had some presentation on quantum computing, quantum machine learning applied to remote sensing, and we tried with some people from the European Space Agency and some PhD students of mine. We tried to present what we have done in the remote sensing. We did something on the SAR images, in the sense that, as everybody knows, SAR images are affected by speckle noise, that is, and disturbance that modifies the images and makes them sometimes difficult to be correctly utilized. And we try to do also something like the speckle filter, but with the quantum inside. So to answer also, to our friend, our colleague, that there are some attempts to include the quantum part inside the classical ways to solve let's say, all the problems in satellite images processing, like SAR despeckling or wrapping or other things. So what we are trying to do is exactly to create some hybrid models in which classical and quantum layers are combined in different ways to improve the outcomes with respect to the literature, to the state-of-the-art results. So we are trying to do something in this sense. Okay, I wanted just to add, because you couldn't attend the session before, so we will share the presentation with you. I want also to ask you to send us what you present about your company, other slides, because we usually share all the presentation with the participants to the school. So thank you about this. I don't know if you want to add something else.
Thank you.
Thank you. Yeah, it's a beautiful example. I appreciate it. I didn't know someone was working on this in practice, and I would love to learn more details. In general, I invite everyone. This is maybe my final comment. I really, if you are working on quantum algorithms or trying to implement something, reach out to myself or to anyone in our company. We would really be happy to know about it and assist you in any way. So that sounds, what you said is a fantastic example, and yeah, I'm happy to try to work together as much as possible. Thank you again for hosting
Absolutely.
me.
Amir, thank to you for your time, for your presentation, and keep in touch, because we want to stay in touch with you. Okay, thanks again for this presentation. Ciao.
Thank you so much.
Next time we want you in presence.
I promise. I will. I want to be there as well. Bye bye.
Ciao, bye.
Bye bye.
Thanks to you.